Okay, spent the last few videos recapping the idea of geometric isomerism, EZ isomerism, which is one form of stereoisomerism. But just to remind ourselves, what is stereoisomerism? The isomers, we've got the same molecular formula and the same structural formula, but different arrangements of atoms in space. Okay, so now let's have a think about this molecule, okay, which is, it's going to be fluorine there, chlorine, a hydrogen, and let's say bromine. So you call that alphabetical order, bromo, chlorofluoromethane. Now, you might be surprised, and most people are, to find that exists as two isomers, two stereoisomers that are not the same as each other. This is misleading writing it this way, isn't it? Because this implies that it's a flat structure, and we know that it's not. The carbon is the center of a tetrahedron. So if I can draw this, right, now I'm going to draw the fluorine going up. So the fluorine is like that. I'm going to draw the chlorine like this. Now the fact that they're solid lines, it means that they're all in the same plane. The fluorine, the chlorine, and the bromine, and the fluorine, the carbon, and the chlorine, they're all in the same plane. Those three atoms would fit onto a flat piece of paper. Okay, but as we know, it's a three-dimensional structure, and so that means I'm going to draw the bromine like that as a wedge, and that means that bromine is coming out from the plane of the screen. And I'm going to draw the hydrogen as a dotted line, and that's to represent that the hydrogen is going back into the behind the screen. So those three, fluorine, chlorine, brome, and fluorine, carbon, and chlorine are all in the same plane. Bromine coming forward, hydrogen coming back, and it's a tetrahedron, and all those bond angles would all be 109.5, wouldn't they? Okay. So the chlorine, the bromine, and the hydrogen would be like the feet of the tetrahedron. The fluorine would be sticking up in the air. Now, if I draw an imaginary mirror down here, so this is a mirror, and I draw the mirror image of that, so I'm going to have the hydrogen going back into the plane of the paper, the bromine coming out towards us, the chlorine in the plane of the paper, and the fluorine in the plane of the paper. So, okay. So these are mirror images of each other. It's if you're like me, it's very hard, and you find it hard to visualize 3D. It's without making a little model of it from your Molly-Mod kits. It's quite hard to play in your mind. But if you try and superimpose this isomer on top of that one, you can't. They're non-superimposable. Okay, so we're going to say these are non-superimposable mirror images of each other. And these are called, they're called optical isomers. They're a kind of stereoisomer. Okay, and the usual analogy here, and it's a good analogy, is if you get your left hand and your right hand, you put them together, they're mirror images of each other. That your two palms fit together. That's what, yeah. But if you try and superimpose your right hand over your left hand, you can't do it. Okay. So that's what we've got there. We have got these are non-superimposable mirror images. Okay. Now, usually there's a lot of some new words in this topic. We say that this carbon here, we say it's an asymmetric carbon. Or people also say that it is a chiral carbon. This word chiral, asymmetric, it means the same thing. Now, what do we need in order to have an asymmetric carbon? Well, if I looked at, let's just change this molecule very slightly. So I'm going to have, instead of having a fluorine and a chlorine, let's have two chlorines on it. So I'll have Cl, Cl, the bromine coming towards you, and the hydrogen coming there. Right, if you drew a mirror image of this one, you would find that it is exactly the same as itself. You can superimpose them. There aren't two versions. So what do you need for a chiral carbon? You need 4 different groups around a carbon. Okay, so let's have a look at another. Let's have a look at another molecule, which will show, which will exist as 2 optical isomers, and you will have heard of this stuff. Lactic acid. Okay, lactic acid. Now, lactic acid can, so it's got a, it's actually really, it's got 3 carbons long. It's got a carboxylic acid group on the end there, and it's got an OH group there, an alcohol group, and this is just 3 hydrogens here. So it's really called 2-hydroxypropanoic acid, but don't worry about that. But if we have a look at this carbon here, you can see that this is asymmetric. Okay, so look at that carbon, you've got 3 different groups attached. You've got the hydrogen, you have got the OH group, you've got a methyl group, and you've got a carboxylic acid group. So that can exist as 2 optical isomers. So if I try and draw that, so let's have, this will be 1 isomer, and you've got an OH going towards you. You've got a carboxylic acid group going into the plane of the paper, and you've got a methyl group in the plane of the paper. I'll draw a mirror. There's our imaginary mirror, and the mirror image of that is going to be, so you've got the carboxylic acid group there, you've got your OH group there, and the methyl group there. So those two different forms of lactic acid, they're non-superimposable. And actually, interestingly, I'm not sure way around it is, but you get lactic acid in yogurt, don't you? And that's made by a bacteria in milk. That's one. And you also get lactic acid in your muscles. Okay, it's a different enzyme in your muscles. It's a mammalian enzyme. This is microorganisms in the yogurt. And they're 2 different forms of 2 different stereoisomers of the molecule. So more about stereoisomerism in the next video.